Okay, in 13.3, we're going to talk about the dot product. So if U is x1, x2, x3, let me just write this, and V is y1, y2, y3, then we really don't have vector multiplication. This is the closest thing to it. We just multiply the first components, the second components, and the third components, and add them together. So 1, negative 2, 4, dotted with negative 3, 0, 1 is negative 3 plus 0 plus 4, which is 1. So the answer is a real number. Now some of the properties of dot product are that U dotted with U is the magnitude of U squared. U dotted with V is the same as V dotted with U, so it's commutative. It's associative or distributive. You can distribute the U, and these are really easy to prove. 0 dotted with U is 0, and if you use scalar multiplication, then you can just multiply one of the vectors by the scalar, or it doesn't matter which one you multiply by, but one of them has to be multiplied by the scalar, not both. So just to prove the first one, like I said, it's pretty easy to show. U dotted with U is x1 times x1 plus y1 times y1 plus z1 times z1, which is x1 squared plus z1 squared, which is the square root of x1 squared plus z1 squared, which is the magnitude of U squared. So it's really easy to prove those properties. Let's go to a definition. Let U and V be non-zero vectors. Let 0A and 0B be their respective position vectors. Then the angle between U and V, the angle between two vectors, is angle AOB. So here's U, which is 0A, and here's V, which is 0B. Then this angle right here is the angle between the two vectors. Okay, further, if U and V are parallel, then theta is 0 or pi. If U and V are perpendicular, then theta is pi over 2. And we call this orthogonal. So another word for perpendicular is going to be orthogonal. Now we can find the angle between the two vectors. By using the dot product. U dotted with V is also the magnitudes of U and V multiplied together times the cosine of theta. That's just an important fact. And we do this with the law of cosines. So if we have 0A 0b, this is theta, this is u, this is v, then the law of cosines says that AB squared is the magnitude of u squared plus the magnitude of v squared minus 2 uv cosine theta. And if we say AB is x1, let's see, x2 minus x1, y2 minus y1, z2 minus z1, then the magnitude of AB squared is x2 minus x1 squared. I'm sorry, I should have had magnitude here. That's just the distance formula. And if we multiply that all out, okay, and we have all that, according to this, equaling u, the magnitude of u squared, which is x1 squared plus y1 squared plus z1 squared. Okay, so in blue, this is the left-hand side. The left-hand side's in blue, and the right-hand side's going to be in red. I'm not going to do anything with that. So you can see these are going to cancel out. All the squareds are going to cancel. And all the negative 2's are going to cancel. So I have x2, x1 minus y2, y1. Well, that's a negative 2. The negative 2's cancel, so I don't need that. So I have x2, x1 plus y2, y1 plus z2, z1 equal u v cosine theta, and that's just u dotted with v. And I'm done. And notice that if theta equal pi over 2, then u dotted v equals 0, and then the two vectors u and v are orthogonal. So that's another important fact. And this is another use of the dot product. The dot product, we can find the angle between the two vectors. Okay, another thing we need is the direction angles of u. Okay, we let alpha be the angle u makes with the positive x-axis. Beta is the angle u makes with the positive y-axis. And gamma is the angle u makes with the positive z-axis. And we call cosine alpha, cosine beta, and cosine gamma the direction cosines of u. So we know cosine alpha is u dotted with I the unit vector dotted with I, so that's going to be x1 over u cosine beta is u dotted with j. I'm using the formula we just got. I'm using this formula from where we just left off. Let's see. This formula right here. But I'm using it to get the cosine. Remember, j is a unit vector in the direction of j. So this is going to be y1 over u, and cosine gamma is u dotted with k, which is c1 over u, where u is x1, y1, z1, which is u cosine alpha, u cosine beta, u cosine gamma. Or you could factor out the length of u and just do cosine alpha, cosine beta, cosine gamma. So that's how it all fits together. Okay, and then we're going to talk about projections. If we have u here, the angle between the x-axis will say theta, and we'll say this is 0b, and this is the vector v. Okay, then this right here is u cosine theta, because that's adjacent. Just call it x. X is adjacent. Cosine theta is adjacent over the hypotenuse, so you just multiply both sides by the magnitude of u. So that gives us that side. So this is the vector projection of u onto v. See, it just kind of projects onto the v vector. The magnitude, or the length, of the vector projection is called the scalar projection, or component of u along v. So the scalar projection is looks like this. And the vector projection is a scalar projection times the unit vector and direction of v. Let me go back to this. Let me go back to this this thing. Remember, the scalar projection was u cosine theta. But remember, u dot v is u v cosine theta. So if I divide both sides by the magnitude of v, then I have this. And that's how I got that. Okay, so this is u dot v over the magnitude of v times v over the magnitude of v. So that's u dot v over v squared times v. So let's do an example. If u is 4, negative 1, 5, and v is 6, 3, negative 2, then I want the scalar projection, which is u dot v over the magnitude of v, which is also u cosine theta, but this is easier to find. So u dot v is 24 plus negative 3 plus negative 10, which is 11, and the magnitude of v is the square root of 6 squared plus 3 squared plus negative 2 squared. That's the square root of 49, which is 7. So this is 11 sevenths for this example. Now the projection, that's in the direction of v. Is the 11 sevenths times v over the unit vector, which is going to be 11 over 49 times the vector v. Okay, so that's how you find those two things. Now let's look at what this is, what we can do with this in real life, a physical interpretation. It has to do with work. Okay, so suppose we have a constant force exerted over distance d. So work is force times distance. So we have this point here along R, and let's say this is S, Q, and this is the force. Alright, so the projection of PQ onto PS is what we need. It's going to move along PR. So we're going to take this box and move it along PQ. So PQ is the same as PS plus SQ. So it's the same as this vector plus this vector. But this does not contribute to any horizontal movement. So the work is going to be the force. So it's going to be the scalar projection of PQ onto PR. That's going to be our force times the distance, which is the length of PR. Now this is going to be PQ times cosine theta times PR and that, using our formula, remember magnitude of U times the magnitude of V times cosine theta is U dot V. So this is going to be PQ, vector PQ, dotted with PR. That's force times the distance. That's going to give us our work, but that's going to be the dot product. That's not times, that's the dot product. Okay, so say the magnitude and direction of the constant force is given by 5, 2, 6. And we want to find the work in moving an object from the point 1, negative 1, 2 to the point 4, 3, negative 1. So we have PR, the distance. Well, first let's find PR. This is P, this is R. Is the vector 3, 4, negative 3. So we do PQ dotted with PR. That's 5, 2, 6 dotted with 3, 4, negative 3. And we get 15 plus 8 minus 18 is 5. And the units are foot, pounds, or if we do metric, it's Newton meters, which is a joule. But here the answer is 5. So the dot product gives us the work done in moving an object if there's constant force applied. Alright, so you can look in the homework to see more examples.